Welcome to this e-learning on device tree concepts and resources. My name is Chelsea and I will be your instructor along this course. But first, let me share with you some of the solutions Intel offers for your engineering projects, as well as all of the resources available for you to explore. The Intel FPGA portfolio supports this transformation, including discrete and integrated FPGAs that are expected to improve processing efficiency, task specificity, and connectivity. Intel FPGAs can provide a variety of workloads in network processing, as well as compute and storage acceleration. They offer greater throughput, execution speed, and energy efficiency than CPUs on computationally intensive parts of algorithms, but with the ability to adapt quickly to changes in algorithms, data patterns, or performance needs. They are available in 5 current families: Max, Cyclone, Aria, Stratix, and Agilex, all with of increasing capacity, performance, and feature sets. The objective for this course is to understand elements and syntax that describe hardware in a device tree set of files and what to add when modifying or adding hardware to your project. This is the agenda for this course. Let's get to a brief introduction on device tree concepts. The device tree is a data structure and language for describing hardware file. It is a description of hardware that is readable by the operating system, which makes it easier for the operating system to know the details of the device and machine. The device tree is organized in nodes. Nodes may have other data that have properties and arbitrary data. It helps provide a way to make usage of board and devices data-driven instead of hard coding. Hardware devices can be discoverable and undiscoverable. These mechanisms help the operating system identify easily the type of device being connected, and not necessarily know ahead what hardware is present during runtime. The devices that are undiscoverable have to feed information to the operating system and bootloader in order to function properly. Not all devices need to be available at runtime. It really depends on the needs for your project, and some are described differently and are brought up according to the needs. Where to find the device tree? The Golden System Reference Design is a great way to get started with device tree sources and files. It provides several resources that build a booting image and help you with your first design as a starting point. To find more information on diverse developments, go to Rocketboards and search for the device being used for a full GSRD description and implementation. These resources can provide a great way to start working with device tree and get to know all of the files required for your image and projects. The GSRD composition, depending on the booting device, includes the following elements provided and maintained for each one of our families in Rocketboards. The GHRD, which is the Golden Hardware Reference designed to be used inside Intel Quartus Prime software with Platform Designer. Linux, which is the Linux Development Repository. ARM Trusted Firmware. U-Boot, which provides the official Intel branch. Yocto Project, which also provides Yocto Project application and customization meta layer for GSRD, as well as Pocky core layers. You can find the release notes available and the latest GSRD composition for each one of our devices at Rocketboards at the Intel FPGA HPS Embedded Software Release Notes documentation. Device tree files are compatible with several operating systems. We provide and maintain the resources to use with Linux OS in our repository, since it is one of the recommended sources for Intel SoC FPGA's development. In this case, we will cover some concepts of Linux OS use of device tree. Linux OS uses the device tree for purposes like platform identification, looks into the compatible property in the root node devices to run specific machine fix-ups at runtime. Runtime configuration, which helps identify the usable RAM size and location among other functions by scanning the device tree during early boot. The chosen node contains properties for platform-specific configuration. Device population is also one of the uses for device tree. Parsing the device tree can help obtain the list of devices and allocate the structures dynamically. By going through the device tree, the kernel starts identifying the devices that contain the compatible property and assumes those are devices that need a driver. The device tree source file is processed by the device tree compiler to convert it to the device tree blob format, which is a binary flattened device tree that the bootloader can use and pass on to the operating system. We have the DTS, which is a device tree source file, another type of file, which is the DTV, which is the device tree blob mentioned, and finally we have the device tree compiler, which can be easily found within the repositories in the GSRD as well as an installation package directly in Linux terminal. Bindings are documents that are specific to each hardware and determine how it should be described inside the device tree. Alongside with the technical reference manual, the bindings provide all the information needed to add to the device tree modification. These are representations of specific types of devices inside the device tree and its requirements. When adding a device to a project, you can create its representation inside the device tree depending on the settings for that device and the use in the project. This means that bindings should be created with the specification of properties and value of the device added. Bindings are provided as part of the Linux OS documentation and can help design and add new hardware description to modify and update when added to the device tree. The compatible property describes the requirement to which that node complies to. It helps the OS determine which device driver to use and needed attributes of the device being described as a new element in the device tree. Index and documentation on how to design bindings are available for numerous devices and architectures with parameters ready to insert in the device tree. This is also available through the GSRD repositories. This is a bindings example, which is part of an example taken from rocketports.org on how to create a device tree. On the left, you can find the required properties described, each one of them, with all the requirements for the device tree entry on the right. It's a simple GPIO with all the properties being described as an entry in the device tree. On the left you can find the detail. Let's take for example the compatible property, which is described specifically as the manufacturer and model in the compatible property on the right with a string directly on the device tree modification. You can also find another example with the number of interrupt cells, which should be 2 as described on the bindings on the left, and then you can find how it is also added into the device tree modification on the right. There is also optional properties like Altera NGPIO 32, which can or cannot be described in the device tree entry. You can also find the specific flags that are supported as part of the device tree entry and requirements to understand all of the hardware that is being added. Please visit the guides on how to create a device tree for each one of the SoC devices in Rocketboard's website. As we saw in this example, the address for the GPIO is part of the information in the manual or specific to a device, but you also need to describe the hardware according to the bindings due to the required properties as determined by the manufacturer and type of device being added to the device tree files. Next, we will cover the device tree composition section. There are different elements that are used as constructs to represent a device tree. These are nodes and properties. We will cover them in detail in the next couple of slides. A node in the device tree has one parent except for the root node, and it is used to describe the devices in the system. A device node is required to describe hardware that cannot be detected by the system, as we mentioned before. Those devices that are attached and detected might not require to be described as nodes in the device tree necessarily. Additional to a root node, some nodes are required for the device tree, such as CPUs or memory nodes that will be described in detail in the following slides. Node names require syntax to describe the hardware and the type of device and unit address. This information can be found easily in the technical reference manual and bindings. The node names have certain characteristics like being 0 to 9 digits, AC lower or uppercase letters, comma, period, underscore, plus sign, and dash only. Here you can see the example which shows a node name EEPROM as listed and the unit address is 51, same as the rec property. Some common names for nodes are ADC, Bluetooth, clock, display, Ethernet, for example, or other common ones include GPIO, I2C, LEDs, among others. We will now talk about the chosen node. It is not particularly described in hardware but used to determine the parameters for the runtime system firmware. On the small square you can see that from the example there are some necessary elements to describe boot arguments for the client and how the console will be sending the information for the output. Slash memory and slash reserved memory nodes are indicating and specifying memory layout of the system. In particular, the slash memory node is a requirement for all device trees. Multiple nodes may be created for each memory range. Reserved memory node indicates in the device tree the memory that the operating system must exclude for normal usage. These are normally used by some special device drivers. In the example, you can find a memory with a unit address of 0 and with a name and device type always indicated as memory and with the rec property. Those numbers in the rec property indicate the ranges that are arbitrary for the physical address and size of the memory and can be found in the reference technical manual. The CPUs node contains child nodes that represent the system CPUs, as you can see here in this example. We can find two child nodes represented with the numbers 0 and 1 as their unit addresses, and each child node needs its particular bindings and description. As you can see here, the device type must be CPU. The rec property is related to the parent's address cells, compatible address cells, and size cells, which will be discussed later in the properties section. Finally, the aliases node defines one or more alias properties, and it is a device's full path to a node. The standard properties are standard ways to describe device nodes and its characteristics. Let's take, for example, the status property, which is one to keep in mind, since some devices need only to be described as OK, due to the rest of the information being present in the device tree already, and by only changing this property the device can be available to use. Some other properties include compatible, which describes the manufacturer and model, and it is a value that defines the specific programming model for the device. Other property is model, which specifies the model for the device. Let's take, for example, Altera SoC FPGA ARIA 10. Fandle, which is an identifier for a node that is unique within the device tree. Rec property, which is an address of the device tree, which we have been also seeing in some of the examples covered. And finally, you can see the status property, which we talked about before. Other standard properties include address cells, which determines the number of cells that encode the address in a rec property. Size cells, which includes the number of cells to encode the size field in the rec property. Each node has its properties to fill out and syntax when describing. There are several properties for interrupts, like interrupts, interrupt parent, interrupts extended, or interrupt cells. Any device that generates an interrupt contains the property interrupts with a value describing the sources or interrupts of for the device. Up to now, different concepts regarding device tree files have been covered. Its definition, some use cases, bindings, and how to use those bindings, nodes and properties, and where all those concepts interact to form the whole description of the hardware in a project. Now, the section of what to add to the device tree will be covered. Some cases when the device tree is chosen to be modified could be when powering up devices after initializing the system to preserve power, for instance. This can be changed in the device tree. Clock frequency variations different than the default configuration. Board customization using the same hardware, but just configuring different device tree versions for each project. If the hardware has special features or requirements that differ from just a regular startup behavior at runtime. For the hardware to be added to the device tree, we need to have some special considerations and keep in mind the bindings related to the description of the device, compatible property to program the device and help the OS find the corresponding driver and bindings, verify the device's address provided by the technical reference manual of the device used in the rec property to define its value. Some other properties might be required to describe the hardware, like mentioned before, address cells and size cells. If you have more than one device, child nodes need to be added and determine the status property. Make sure to include .h files for the overlay or DTSI for modifications. There are different ways to update and modify the information for the Linux OS after the device tree entry has been modified. This needs to be done for the system to apply the changes and start working with the device added. A driver is the software that controls a specific piece of hardware being described by the device tree to it. It is important to update the drivers for the Linux kernel to identify the devices present at runtime and their configuration. The information in the device tree must match that one being also used for updating the driver, as well as any additional information to add. Some of the functions will be described later in detail in the following slides. This next section in the agenda will be about compiling and using the device tree. For you to understand the device tree source file, it needs to be converted into the device tree blob or DTB file. It is also known as a flattened device tree, and it is a binary file used to indicate what hardware is present in the system. The compiler is located in the Linux OS kernel tree under the location scripts/DTC, or you can also download it using a package manager in the Linux terminal. The device tree compiler converts from or to any of the following formats. Input formats are DTS, DTB, or FS, which is a proc device tree style directory. Output formats are DTS, DTB, or ASM assembler source. You can, for instance, compile a DTB and have an output format of DTS. You can use from or to any format as input or output. As mentioned previously, to use a device tree with a Linux OS driver, it must be updated. You can manually install the driver in the appropriate directory after being built or install it. The Linux kernel's device tree framework parses the device tree data and passes it to the appropriate driver. To use a device tree within the Linux OS driver, you can use some of the functions provided by the Linux kernel's device tree framework. Let's take a look at a couple of those examples. OF_match_device, which matches a device tree node to a specific driver. Let's take a look at another one. OF_device_ID, which is used to call the device information in the device tree. You can take a look at other examples in this slide. This is an example of a Linux OS driver and device tree. It's taken from the strat_extend example inside Rocketboards. As you can see on the left, this is the device tree GPIO hardware section. And on the right, you can find the Linux OS driver GPIO in altera.c file driver. As you can see here, the sections use the hardware description in the device tree to construct driver within the functions mentioned. The GSRD flow in rocketports.org produces the files necessary for the system being targeted to function. In this case, you can find the strat_extend development kit build that contains the complete DTS file and the corresponding driver with .c extension that match all the peripherals present in the device tree and available to the system. The next section will describe how U-boot takes the information from the device tree. U-boot is also known as a universal bootloader and works with the device tree to pass information on what devices are present in the design. Additional to the device tree, U-boot also uses the kernel image to boot the device. Both are binary files. U-boot uses the device tree blob, passing the information through R2, and there is no need to specify machine type since it contains the description of hardware previously specified by the kernel and ATAX pointer. The command for U-boot is shown on screen to be used and pass on the information for the device tree blob. The device tree blob file is a single pointerless data structure can contain information in a certain order. Some of the elements of the data structure are the header, the memory reservation block, the structure block, and the strings block. You can find some resources and references in the following section used during this presentation and if you want to learn a little bit more about device tree and modifications. Intel provides multiple avenues in which to learn about Intel FPGA products. There is the Intel FPGA YouTube channel which contains 5-minute quick videos along with longer, more in-depth training videos. There is the Intel FPGA training website where you can access learning courses made up of narrated slides presented in an interactive player, some courses with labs and demos. Lastly, you can also enroll in a live instructor-led course virtually over the web. All instructor-led courses have hands-on lab exercises to practice the concepts you learn. If you need more assistance, Intel provides many self-help resources for you to access. Intel FPGA Technical Training Team is continuously looking for ways to improve our training. Please email with any thoughts or comments to the following email addresses.